Okay, we're now finished with the acidity of salts, and I will give you a homework assignment later dealing with them. We're now going to get into one of the most important topics in acid-base theory, and that is something called titration curves. And it's going to take us actually 2 lectures to get through them. Now, there are 2 types of titration curves we're going to consider. One is a strong acid reacting with a strong base. We're going to do that one today. And on Thursday, we're going to look at a weak acid reacting with a strong base. There are other possible combinations. We'll only consider these 2 in Chem 1B. Okay, now first of all, I've got to explain what this is all about. Okay, so I want you to look at the diagram on the right-hand side. Okay, so we're going to deal with the strong acid, hydrochloric acid. And as an example, it's going to be 10th molar. There's going to be 50 milliliters in a flask. Now, above the flask is going to be a burette. That's my crummy drawing of a burette. Okay, and the burette is going to be 10th molar sodium hydroxide. So the strong acid is hydrochloric acid. The strong base is sodium hydroxide. Now notice in the flask is a pH meter. And that's important because what does a titration curve look on the graph on the left-hand side? It's a plot of pH versus milliliters of sodium hydroxide added. So what's going to happen is we're going to slowly add sodium hydroxide, and we're going to calculate what the pH will be. So we're going to get something, a titration curve. Not going to look like this, but just give you an idea. That is the goal of how we're going to do this. Now, the first thing we're going to do is we're going to lay out the graph. Okay, so I printed out a blank graph for you. Okay, so I want you to take this graph and put it off to the side because we're going to use it. As we come up with data, I want you to actually draw the titration curve yourself on this graph right here. Okay, now the first thing we're going to work out is the x-axis. Okay, now the end point, sometimes called the equivalence point or the neutralization point, is where the moles of the acid equal the moles of the base. Now, you've seen this in lab, you've probably seen it many times before also. The basic titration equation is this: the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. When this equality is true, that's when the moles of acid base are equal to each other, and that's called the endpoint. Okay, with the numbers we have, then the molarity of the acid is 10th molar, and Berg decided you're going to have 50 milliliters of it, so that was in the flask. Okay, now we're dribbling in 10th molar of base, and X represents the volume of base that will be needed to reach the endpoint to neutralize all the acid. Now notice I picked pretty nice numbers. I mean, you can almost eyeball this. 0.1 times 50 equals 0.1 times 50. Yeah, so 50 milliliters will be the endpoint. So we're going to calculate the pH at the endpoint. We're also going to get it at the midpoint. So halfway through the titration would be 25 milliliters. And to get the overall shape, we're going to also do this at 100 milliliters. We're going to get the pH at these 3 points. Now, I'm going to write these in. Anyway, why don't you go back to this graph here, and why don't you label the dark line as 50 milliliters, that's the endpoint. Estimate about halfway through, label that as 25 milliliters, and then double the endpoint way out here would be 100 milliliters. Okay, so you've now labeled the x-axis. So we're going to get pHs at these 3 points. We're going to get a few more points also. We're going to get it at the beginning of the titration also, and some other points also. Okay, so now we're going to calculate some pHs. Now the pH at the start is pretty easy because all we have is 10th molar hydrochloric acid. It's a strong acid. It's going to break up to give you 10th molar hydrogen ions. Okay, and minus the log of 0.1 is, yes, the starting pH will be a pH of 1. Okay, now from now on, it's going to be a little bit trickier. Okay, we now need to calculate something called the titration equation. Now, let's review how a neutralization reaction works. So we have hydrochloric acid, a strong acid, mixed with sodium hydroxide, a strong base. Okay, and neutralization is going to give us water and a salt. The salt will be sodium chloride. Now, converting this to an ionic equation, there's no such thing as a molecule of HCl. It breaks up into hydrogen and chloride ions. Sodium hydroxide breaks into sodium hydroxide ion. Water, you recall, mainly is going to be a molecule form. Most salts are going to ionize against sodium and chloride ions. Okay, now notice I put in red, I marked off the spectator ions. So the basic titration equation, the ionic equation, that equation, hydrogen plus hydroxide gives us water. Now we need the K for that reaction in order to do calculations. So K titration is never going to be on a table. You always got to figure it out for yourself. Okay. Now if you look at this closely though, look at the reverse reaction. It's water breaking up into hydrogen hydroxide. That's a K sub W reaction. So remember, if you want to calculate the forward reaction, but you know the reverse, it's just a reciprocal. So it's 1 over K sub W, 1 over 10 to the minus 14. So the K for our reaction is 10 to the positive 14. Now, we've got a double check here. Titration reactions are always favored. Why? Acid always wants to get together with base, so you should always end up with a positive value. Okay, we're now going to calculate the pH halfway through the titration. So you've got your net ionic equation. Hydrogen plus hydroxide gives us water. Now let me write some numbers there. Okay, so we have 10th molar hydrochloric acid, 50 milliliters of it. We're going to mix it with 10th molar sodium hydroxide, 25 milliliters of it. Now, when you mix two solutions together, you must take dilution into account. So the total volume is 75 milliliters. So dilution factor is 50 over 75 for the acid. 50 over 75, you're working on a calculator, is about 0.066 or 0.0067. Okay, going to the hydroxide, 25 over 75 is 1/3. 1/3 of 0.1 is 0.003 molar. So at the start, we have diluted acid, 0.067, diluted base, 0.003, and no water yet. Okay, the completion step is going to be to the right because of the large size of the K. Now, it's a 1-to-1 reaction, but the base is a limiting chemical, so all of it gets used up. So you have 0 after the completion step. Now, in the case of the acid, it's a 1-to-1 reaction, so 0.033 of the acid is going to be reacting, leaving an excess of 0.033. And water is going to form also, even though we don't really need it. Okay, now look at the change step. In the change step, it's going to go to the right. It's favored to the right. And what's going to happen, you're going to have some excess acid. Now, you can't have a 0 in an equilibrium system, so now the change step is to the left. So now some water reacts minus X to give us some positive X base and some positive X acid. So at equilibrium, the acid concentration is 0.033 minus X. The base is X. Now, we could solve for the hydroxide ion concentration, the pH concentration that way. We're not going to do that. Let's solve for X for the moment. So go to the K, which is 10 to the 14th, and plug this into the mass action expression. So water, we write a 1. For the acid, 0.033 minus X, and for the base, X. Notice I cross off this X with a red line. Now, if you solve for X, you can answer 3 times 10 to the minus 13th, which is really, really small. And therefore, the hydrogen concentration is 0.033 minus X. The X doesn't even show up. So the hydrogen concentration is 0.033, and therefore the pH is minus the log of that, 1.48. Now, I've taken you through this based on first principles. It's way, way too much work. This is what we're going to do from now on. Go back to the completion step. We're going to base the pH just on the excess acid or the excess base. What I try to show you is X is so small we can ignore it. So therefore, we could have stopped at the completion step. I'll draw a line here. We could have stopped right here and based the pH on the excess acid. Okay, I'd like to show you the titration curve so far what we've had. There we go. Okay, so here's the titration looks like so far. Okay, so at the start we found out the pH is 1. We've gone to 25 milliliters added halfway through the titration. And the pH was 1.48. Okay, now here's what I want you to realize. Okay, We've gone halfway through the titration, and the pH has changed hardly at all. So far, it should look kind of boring to you. That's okay. Okay, next we're going to add 49 milliliters of sodium hydroxide and calculate the pH. Okay, so let me get to that screen. Okay, here we go. So now I'm kind of chicken to go to the endpoint right away. So I'm going to just add 49 milliliters of sodium hydroxide. We're not going to get to the endpoint yet, so I just want to go to 49 milliliters. Okay, now go through the mathematics with me. Okay, so the net equation is hydrogen plus hydroxide gives us water. Okay, so for 49 milliliters added, here's the mathematics. It's 10th molar in hydrochloric acid, and we have 50 milliliters in the flask. Berg wants us to calculate the pH when we have 10th molar base in the burette. We're going to add 49 milliliters. Now, we have to take dilution into account, so the total volume is actually 99, but we're just trying to get the shape of this thing. So let's make the total concentration 100 milliliters, about 100. Okay, so taking dilution into account, the diluted concentration of the hydrochloric acid is 0.05 molar, and the base is 0.049 molar. Okay, now the completion step is to the right. Notice the base is the limiting chemical, so all of it gets used up. So after the completion step, there's zero of it, but there's a little bit of excess acid. Now you see this blue line? The reason I drew the blue line is because I tried to show you the last time, we don't no need to go further. No need getting X. We can base the pH on the excess acid or base. Okay, so look on the right-hand side. The hydrogen concentration is 0.001, which is 10 to the minus 3, and therefore, the pH after 49 milliliters is 3. Now, look at the bottom part of this sheet. I'm still kind of chicken to go to the end point yet. So now I want to find out the pH we got at 49.9 milliliters. Okay, so let's look at the mathematics again. So the initial concentration of the hydrochloric acid, 10th molar, 50 milliliters of it. Okay, the base is 10th molar. Berg wants you now to add 49.9 milliliters. We have to take dilution into account. The total volume again is about 100 milliliters. So doing the math on that, the diluted concentration of the acid is 0.05 molar. And notice what the base is, 0.0499 molar. It's the limiting chemical, so subtract that from both sides, or from both chemicals, zero base, and notice the excess acid. We do the subtraction, you get 0.0001 molar. Look on the right-hand side. So the hydrogen concentration in scientific notation, 1 to the minus 4. If you don't have a calculator, okay, the pH is 4. Okay, I'd like to transfer these numbers now again back to the titration curve. So you should get out the sheet of paper where you have the titration curve, and let's transfer these numbers over there. Okay, so here we go. So we have the pH at the beginning, which was 1. Halfway through, it was 1.48. Now, I'm going to go to 49 milliliters, and the pH was 3. Now, here's the startling thing. We've gone through 49 milliliters of sodium hydroxide. The pH has hardly changed at all. By the way, this is actually part of experiment number 9, where you actually do this in the laboratory, where you dribble in the sodium hydroxide and you record the pH after every milliliter. I don't have students do this anymore. You know why? Students kept falling asleep. It's boring. It's boring until you get close to the end point. Now we're getting some action. So at 49.9 milliliters, the pH was 4. So now we're getting some action. Okay, let's do some more calculation now. But so far, it's boring until we get close to the end point, and now we're getting some action.